we now have Eduard, who is a postdoc at MBZUAI. Eduard has some amazing work in optimization. I've known his work since a few years actually. He's got some amazing recent, just unrelated to the workshop. He's got some really cool work on variation inequalities, which anyone's interested, check it out. And today I think he's talking about Byzantine-robustness.
Thank you, Pranit, for the introduction. And it's my pleasure to present our recent paper called Variance Reduction is an Antidote to Byzantines and better rates and so on. And this is a joint work with Samuel, Peter, who are here, and Mathieu, who is in Canada. And yeah, here is the outline of my talk. First of all, I will introduce the setup of Byzantine-tolerant training. Next, we will discuss robust aggregation, and then we will focus on variance reduction as an idea to cope with Byzantines. So let's start. And let me briefly describe the problem. So it was already mentioned multiple times today. So we consider a parameter server setup where we want to minimize average of n functions. And n here is number of workers. They are connected with the server in centralized way. And x are parameters, d is the dimension, number of parameters. Fi is the loss function which is stored on worker I. So it's loss function constructed using the data on worker I. And in the Byzantine-tolerant training, the key features are that individual participants, they can be weak in terms of computation, and they not necessarily know each other, so they do not trust each other. And the simplest method to solve such problem is parallel SGD, but we will see that it is not good method for such problems. So in parallel SGD, let me remind you that at each iteration, server sends the current parameters to the workers. They compute stochastic gradients, namely unbiased estimates of the true gradients of their local loss functions. And then they send it back. And server averages stochastic gradients and makes an SGD step. So everything is classical, simple. But this method is fragile to malicious peers. So if, let's say, the third worker sends, instead of the stochastic gradient, sends something else. For example, this worker can flip the sign of the vector. The worker can flip label or just send some random vector with very large variance. This way, this worker can destroy the whole average. And so basically, this vector can be arbitrarily bad, and average can be arbitrarily bad, and our method will diverge or will not converge, which is enough for malicious peers. And basically, we should slightly change the formulation. First of all, as I said, we have good workers, which is denoted by G, and we have bad workers. Bad workers here, we will call them Byzantines. It has some relation to Byzantine general problem, and we assume that number of Byzantines is strictly smaller than 1/2 of workers. And we assume that Byzantines are omniscient, so they can know everything. All right, and next, we also cannot assume that local loss functions are arbitrarily heterogeneous, because if we assume that they are arbitrarily heterogeneous, then basically we cannot distinguish between good and bad peers. And basically that is why we need to assume that Byzantines form minority. Otherwise, we also cannot understand who are good and who are bad. And in this talk, we will focus on a special case of the discussed problem when all local loss functions are the same. So in some sense, it's meaningful assumption for this setting. And in the paper, we have some generalizations as well. But you can think of it as of the case when all workers have access to the entire data. And how to solve such problems? It's a natural question. And basically, I will mention just few works. There are many works on that topic, and many works focus on robust aggregation. So basically, the natural idea is to replace averaging in parallel SGD by some robust aggregator. And I haven't defined yet what is the robust aggregator, but let's consider some examples first. And they so-called middle seekers aggregators, like geometric median, which requires to solve auxiliary optimization problem. It's arg minimum of the sum of distances to the vectors. Or you can do the same, but coordinate-wise. It's called coordinate-wise median. By the way, geometric median in the literature, it's called sometimes robust federated averaging. Or there is another popular estimator called CRAM estimator. Basically here, we pick the worker with the smallest score. What is the score? Score function, it's a sum of square distances to the n minus b minus 2 closest workers to that worker. And this kind of aggregators, they work well in the following cases. For example, consider the situation when Byzantines try to create outliers. Like we have 4 good workers with values 1.5, 2, 2.5, 3. And Byzantine is one-dimensional problem. And Byzantines, they are sending values 1000. So if you compute average of the good workers, it will be 2.25, some small number. If you compute average over all workers, it will be 335, much larger than average over good workers. And median and CRAM, they will be close to that average over good peers. So in this case, we can say that if outliers are something undesirable, then middle seekers can be good for reducing the effect of outliers. But in some problems, outliers naturally appear, like if you have heavy tail distribution, like in NLP tasks, or if you have imbalanced data. And basically, these examples are taken from Pranit's recent work, ICML 2021. And also, there are some state-of-the-art attacks that show bad things about middle seekers. So you can create the following example. Assume that blue dots are correct workers, like good workers. It's stochastic gradients of good workers. And they have true mean, which is red star. And Byzantines, they try to hide in the noise. So basically, they compute average of the good peers and like compute coordinate-wise standard deviation, and then they choose value z in such way that their values are on the edge of that cloud. So in this case, if you have symmetric distribution, then Byzantine workers, they have some supporters nearby, and also there are some opposers on the opposite side of this cloud. And basically middle seekers like geometric median, they will interpret opposers as outliers, and then they will not take them into account. And this is intuitive explanation why the aggregator will return shifted value. And this is called a little is enough attack by Baruch et al. It's NeoRIPS 2019. And in the same work, the authors show that basically parallel SGD without any defense, just with with averaging is more robust than these robust aggregators. And yeah, so it means that first of all, we should somehow change the methods, and secondly, we need to finally introduce formal definition of robust aggregation, and it was done again by Pranit and co-authors in the same work, where they introduced the definition of delta C robust aggregator. So basically, what does it say? It says that if your good workers, they have some bounded variance, let's say pairwise variance, then we will call aggregator delta C robust if this inequality holds. So here G hat, it's aggregator, output of our robust aggregator, and G with overline, it's average of good peers. And delta is the ratio of Byzantines, and sigma is noise level. So basically, it makes sense because if your variance is very high, then you cannot actually rely on the good accuracy of your aggregation. You cannot have good accuracy of aggregation. And also, if you have a lot of Byzantines, you also the quality of your aggregator should depend somehow on this delta. And in the same work, they proved that actually this definition is tight up to a constant, and middle seekers, they do not satisfy this definition, and basically, but one can fix them using another trick called bucketing. It's another work by Pranit and co-authors. It's iClear 2022. And basically in bucketing, we want to robustify some aggregator. And what we do, like in bucketing, first of all, we permute workers, then we split them into buckets and compute average in each bucket, and after that compute aggregation of those averages. And one can show that basically gram, geometric median, and coordinate-wise median, they, after bucketing, they satisfy the definition of delta C robustness. And moreover, they do not depend on the noise level. Like these estimators, like parameters, they are agnostic to the value of sigma square, or to the noise level, and which will be important for our purposes. Okay, and so I will not cover methods that already use this formalism. I will just move on to the variance reduction, because it's the main goal of this topic, of this talk, to cover this idea. So, and the idea is very simple, like, and very natural. So if you have very large variance, then for Byzantines, it's really easy to hide in the noise, and really easy to create large bias. But if you use some method that, like variance reduced method, let's say, that reduces the variance of stochastic gradients, then it becomes progressively harder for Byzantines to somehow spoil the convergence. And this is the idea. So if your stochastic gradients are well concentrated, Byzantines, they cannot do anything. And basically, one intuition says that even middle seekers should work well on those examples. And yeah, in the work by Wu et al., they proposed Byzantine-robust Saga. So they took parallel SGD with robust aggregation, but instead of the naive SGD estimator, they use Saga estimators. And that's it. So in this case, under some classical assumptions of strong convexity and smoothness, they proved the following complexity bound. So basically, if delta is smaller than 1/2 ratio of Byzantines, then BERT Saga or Byzantine-robust Saga with batch size B finds point xk such that it's epsilon solution in expectation after the following number of iterations. So let's look closer at this bound. So basically, let's focus on the case when we have batch size 1. Here, M is the number of data samples. L over mu, it's a condition number. So even when we have 0 Byzantines, complexity is proportional to M squared times condition number squared. So, but usually condition number and M, they are very large. And squared, and if you multiply them and then squared, then you will obtain very large number. For example, complexity of Saga is much better. I mean, in the ideal scenario, it's much better, M plus L over mu. What is the issue that prevents BERT Saga to have similar complexity result? Of course, we have Byzantines, but still, why so dramatic deterioration of the rate? And the answer is that Saga and Saga-based methods and SPIR-G-based methods, they are very sensitive to biasness. So basically, the analysis, it relies on unbiasedness. But if you apply some robust aggregation, you lose unbiasedness. And at least all known robust aggregators, they are biased. And this is the key issue. But what you can do? Okay, robust aggregation, it breaks unbiasedness. But if you take something that is already broken, like biased variance reduction, it's not broken. It's like unbiasedness is broken. But if you take such kind of methods, then everything should be okay. They variance reduced, and biasness doesn't change anything there. Okay, and biased variance reduced methods, they look like SGE, but GK is defined as follows. With, for example, it's geometric Sara or page estimator. This was proposed by work by Samuel and Peter and Mike, and also in the recent work by Peter and his postdoc Giseli, and also Sara. The idea of Sara was proposed much earlier in the group of Martin. Yeah. Basically, here the estimator is defined on the slide with some small probability. We compute the full gradient, and with large probability we compute just stochastic gradient difference and add it to the previous estimator. And if you choose probability in a nice way, then expected cost, computation cost of this of computing GK is the same as of computing the second case, like the second option, basically up to some constant. And in this case, you already do not have unbiasedness property, but the algorithm works. So what did we do? We just asked good workers to compute these estimators, page estimators. And on top of that, server takes a robust agnostic delta C robust aggregator, which is agnostic to the variance. And that's it. So this is the main idea of the new method, which is called Byzantine-robust page, but in our paper it's called differently. It's called Byzantine variance reduced MARINA, and I will explain why. And we obtain the following complexity result. So in the non-convex setting, we proved that the new algorithm finds epsilon stationary point after the following number of iterations. So basically, it's as expected 1 over epsilon squared dependence. It's optimal in terms of epsilon, and it also this complexity result is optimal when delta equals 0. So, and also we show in our work that this result in this setting, it's better than previous state-of-the-art theoretical result. And open question here is this result optimal? Because we know that it's optimal when delta equals 0, but still in this setting there are no lower bounds in Byzantine-robust training. And we also have extension, like cherry on the top, to communication compression. So basically, as Martin explained, if you compress something that goes to 0, then it's okay for the method. And in this case, the difference between stochastic gradients, it goes to 0, and so we can easily compress it. And actually, without Byzantine-robust stuff, it was done in our previous work, also with Konstantin Polachenko, Żyzeli, and Eduard. And we also tested the proposed method on logistic regression tasks. And in this case, as expected, we also have a result in PL setting where the method has linear convergence. And as expected, we observe it in our experiments for all tested attacks. So it's green line, it's a linearly converging algorithm. Basically, it's Byzantine variance reduced MARINA. And to conclude, I just discussed today a very simple, simplified version of our results. We also have analysis in the case of compression, analysis under bounded heterogeneity, also non-uniform sampling of stochastic gradients we consider, and our analysis takes into account some kind of data similarity, and we also have additional experiments. Yeah. Thank you. And now I will be happy to answer your questions.
Maybe a quick one.
Yeah.
So if I understood correctly, it wasn't clear to me whether the analysis was done under the IID assumption or
You mean by IID? You mean
the expected gradient of everyone is the same?
yeah, we have an analysis under the assumption that all local loss functions are the same. Like each client can compute full gradient of f, but we have analysis also in more general setting under bounded gradient dissimilarity assumption.
So, should I think of this with probability P full gradient? Should I think of it as that involves a communication step across everyone, or should I think of it more as locally the full data set is available?
In this simplified case, yeah. So everybody has access to the whole data, but actually, in practice, it can be implemented like if you have streaming access to the data, so they can download it while running the algorithm. So, yeah. But still, this setup it's also justified. So there are some examples of like real-world training where collaboratively agents, workers, they train some large models that they cannot train separately. Like some language models, let's say, for, I think it's called Sahaj Bird. I think, if I'm not mistaken, for Bengali language. They trained it collaboratively.
Yeah, makes sense.